sectors, maybe 1 hour, and then we move to the geological department to see some thin section of rocks, some practical exercise. Okay, have you a good lunch? Dal bat, pasta, spaghetti, pizza. Uh, Different kind of food, but nice. A little bit spicy, in India. For us, but it's good. Uh, You see the fish? Wow. Which is the right one? Ah, okay. Ah, okay. Watch it. Okay, in this picture, you can see the development of the fabric in the shear zone with the kind of rocks. So, in this graph, you have the gamma, the shear strain, but you know very well what is the shear strain now, the angle theta prime, the angle of the x-axis of the strain ellipsoid with respect to the shear zone. So with increasing strain, you can see an increase, the red line increase of the axial ratio of the x became much more elongated and the z became shorter and shorter. So the axial ratio increases a lot. Whereas at the same time, this angle decreases up to parallelize to the shear zone boundary. So if we can start with deformation, we can we are now in this point, no deformation, no theta prime 45 degrees, gamma 0. So the fabric of the rock is like this. This is granite, isotropic deformation, no preferred orientation, no foliation, no lineation. But if we start to deform, we have gamma 1, so the angle is 45 degrees. The axial ratio is around 2, 3, 4. Okay. Okay, and you can see the fabric of the rock start to change. The rock is foliated. These crystals are elongated, shorter than elongated in this direction. There is a defoliation wrapping around this crystal because maybe it should be feldspar, much more stronger than the matrix. In the matrix, you have quartz, biotite. So there is a preferred orientation and a strong foliation in the rock with increasing strain. Gamma is this point. Axial ratio increases, and the fabric is much more pronounced with a very strong elongation of the crystal. When gamma reached the 6 and the axial ratio, boh, avanti per conto suo. Okay, in this situation, the axial ratio is nearly 40, 50. That is very, very high amount. You can see a rock that look like strips. You cannot recognize easily the axial ratio because the elongation is maybe 50 meters and 1 meter in thickness. So it is difficult to recognize the object in the field. You have to see the outcrops in 3 dimensions, and there is a strong foliation, and the rock is quite different to the starting point. Okay, so if you are in a very big shear zone, maybe thick 5 kilometers, and you walk on this rock, you cannot see at first sight that is a shear zone. You cannot to walk towards the wall and to observe the gradient of the formation, and so you become aware to be in a shear zone because to be inside and observe only this part, it is very difficult. So to recognize the original rock, mm, because this rock can derive from granite, from gneiss, from migmatite. So different kind of rocks can form this mylonite. and increasing deformation. If you move in this red point, axial ratio is very, very high, and gamma is around 13. You can have a rock like this. So very, very deformed rocks up to maybe this kind of rocks. Maybe this kind of rocks contain some melts. So the fabric is totally changed. So this is what happens when the formation increase and fault rocks and magnetic rocks develop in a shear zone. So it is very important. For example, when I was the first time inside the main central thrust in Nepal, that was with a thickness of 5 kilometers, I was not aware to be in a shear zone because you have to walk towards the upper part, the greater Himalayan sequence or lesser Himalayan sequence, to observe a decrease in the formation, a strength gradient towards the south and towards the north. In this way, you can be aware of the shared zone and to understand fully the rocks that you are observing. Yeah. Uh, this one. Uh, Okay, you can produce this kind of fabric with pure shear, simple shear, or both. So the fabric itself is not indicative just from the picture of the kind of deformation. You have to go inside with some vorticity analysis to detect the amount of pure shear and the simple shear inside. Because the final result is the same if you start from simple shear, pure shear, or combination. Okay. Okay. Now, tomorrow we will go into depth to distinguish in between the different shear zone. But now we stop with the shear zone and we start to uh, to describe kinematic indicators. So we will try to recognize them later in this section. Okay. That's the problem. Okay, the main kinematic indicators that we can use in a shear zone are deflection or transposition of pre-existing marker or foliation. We saw before some dikes intruding the shear zone, then displaced. These are beautiful kinematic indicators. Then one of the best is the shear band cleavage, the SC prime cleavage that probably you know. This picture on the background is from a leucogranite deformed in the South Tibetan detachment in southern Tibet in a granite showing S and C fabric that will be described after. Then the oblique foliation, asymmetric porphyroclast, quarter structure, and asymmetric boudinage. They are the best kinematic indicators that we can observe both at the mesoscale and at the microscale. Okay, the SC fabric is very easy to recognize because it is very common at the outcrop scale. So it not necessitate observation under the microscope. So it is um, very easy and very good. Okay, the S fabric, if we give a look to heterogeneous shear zone with undeformed block and heterogeneous deformation inside, you can see the circle and the strain ellipsoid. The strain ellipsoid mark the trajectory of the foliation. That is the x epsilon plane of the strain ellipsoid. So the foliation has this shape across the heterogeneous shear zone, this one. And this is the S fabric. That means schistosity from the French word schistosité, studied by structural geology in 1979, Berthet, Chocrun, Guzzo, because they found in a granite in Armorica in France a shear zone cross-cutting Variscan granite. The Variscan granite was undeformed, but inside the shear zone were developed a beautiful S and C structure. And at up to that moment, people believed that exfoliation was linked to a previous tectonic event, S, and the second tectonic event produced the C fabric. And in 1979, there was the first paper demonstrating that S and C were produced simultaneously at the same time inside the shear zone. It was a very important discovery for such a geologist. The first SC structure were observed in ice in maybe 1971, because some people studied sheared moraines and they found in ice crystals a fabric like SC, but such a geologist needed 8 years more to understand this kind of deformation in the rock. So SC fabric is made by S foliation with a sigmoidal shape that mark the XZ plane of finite strain. Sorry, the uh, X epsilon is the section, this is the foliation. And the other plane is the C plane, it is one, straight one, that is parallel to the shear zone boundary. And the SC fabric is replaced at the scale of 1 centimeters, 2 centimeters, and it is a little mm, smaller shear zone with the same geometry. So this kind of shape, this S with this C, indicate a dextral sense of shear because you have elongation direction x and shortening direction z in this uh, uh, in this position in this geometry. Okay, if you have a sinistral sense of shear, this ellipsoid should be completely reversed in this direction. So the orientation of the ellipsoid and of the S plane give an indication of the shear sense. So you can have a steeper orientation here, then the line is leaning to the SV plane, the upper part, and the opposite part in the lower C plane. So this geometry is characteristics and indicate a dextral sense of shear. Okay, this is more or less what I said. Okay, with the evolution of the shear zone, with the increasing shear strain, the strain ellipsoid start at 45 degrees in simple shear, then rotate towards parallelism to the shear zone. So at the end, after a certain amount of time or large gamma strain, the strain ellipsoid is oriented in this way, with direction parallel to a shear zone. This means that I am elongating the shear zone, and the structure that accommodate this elongation are the C prime extensional shear band. The C shear band are like this. The C prime are synthetic with the same sense of shear, the same arrows, but inclined at 15, 20 degrees with respect to the shear zone. And these C prime extensional shear zone are less continuous and occupy only few millimeters, centimeters the shear zone, but are indicating the same sense of shear. Okay, this is a classical view of the C prime structure, but there is a nice numerical model by Melanie Flinch, a female Australian geologist modelizing a deformation that found that the C prime shear bands are ephemeral. That means they form continuously during the deformation, but they are created, then disappear continuously all along the history of a shear zone, not only at the end. But the sense of shear is the same. If you would like to observe the movie from the experiment from medical models, you can go to YouTube channel. Uh, you can also find Melanie Flinch C prime, but also if you use this link, you can reach the movie that is very very nice. And this paper has been published on the Journal of Structural Geology 2020. Okay. Okay, these are some pictures from Pasquier and Trau, the book. You can see the SC shear bands, the C prime shear bands, and usually in the light that the C prime shear bands develops at the end, in the inner part of the shear zone, you can observe that during deformation, because the shear plane is an attractor of the plane, the lines, also the S and C uh, try to become parallel with increasing strain. So at the end, you can have SC with the same foliation, the same line, and the C prime develops obliquely to the shear zone boundary. To recognize correctly C and C prime, you have to know the shear zone boundary, because otherwise in the field it is not so evident. This is a small movie by Hakon Fossen that he adopted the interpretation that C prime develops at the end of a shared zone. So S fabric, C fabric that is much more continuous, and C prime that is a little bit discontinuous with small planes in the shear zone. Is another view of the C prime shear zone, and you can see that in a sinistral shear zone, all the object rotate to the left, but to develop C prime, this part has a counterclockwise rotation, an opposite rotation, just to accommodate this kind of object. Okay, is a shear zone, Carboniferous granodiorite in the Roses, Spain, close to Barcelona, a very nice place because there is good food, paella, there's the rice with fish, meat, very good, good wine, and also beautiful shared zone. We are sometimes with the students to observe because it is along the seaside with very fresh outcrops, very clean. So what you can recognize is an S fabric, this one. You can see more or less granodiorite. Granodiorite means feldspar, biotite, quartz is S-shape foliation and S and C foliation. This shear zone has been studied by several authors in the 80s, especially from United States, Simpson and so on. So they are very famous. Okay, so according to what I said what is the sense of shear? Dextral? No? Sinistral? Left? Yes. Sinistral sense of shear. These are beautiful. C plane. In this point, we cannot say if it is really a C or C prime because we cannot see the boundary of the shear zone. So to be safe, we call C and S, but if we can observe the boundary of a shared zone, probably this is C prime. But in the picture, we cannot say because we have no information about the boundary of the shared zone. This is a beautiful outcrop, famous outcrop named oyster shell. Oyster is a fossil, more or less. We are in the Moyne Trust in Scotland because you can observe this white stuff are quartz crystallized along sea structure. So the shape is like an oyster. And at the end of the 18th century, there was a long debate about the contact in between the Lewisian rocks and Moyne rocks. And some people believed that there was a stratigraphic contact, but mm, L- Lapworth was the first who recognized myelonitic deformation in scene section because he collects scene section along this kind of outcrops, and he found decreasing grain size in the rocks, and is started to suppose a tectonic contact. And it's that really it is a very beautiful tectonic contacts with myelonites, quartz rich myelonites, and C prime structure that is the so these are not fossils, but quartz vein crystallized along the exfoliation with a curved shape. So we have the C plane like this, the C and the S line, and the sense of shear is top to the right. Ecco, in this case, we don't see the boundary, but we can see one plane and one plane with an angle of more or less 15, 30 degrees. So we can say that they are exactly not the same plane, but two plane with a small angle, indicating the same sense of shear. This is a picture from the book of Fossen that we can download directly from separate file. Also, is a beautiful myelonite in Antarctica with C, maybe C prime, and S fabric is beautiful, very beautiful development of this kind of fabric, and also some rotated porphyroclast like this, or this one. But the sense of shear is clearly up to the left. Okay. We are in the island of Sardinia. These are Paleozoic rocks, maybe Silurian rocks deformed during the Variscan orogeny that happened during the lower Carboniferous by collision between Gondwana and Eurasia. What you can see here, some CS structure. Why not? Maybe this one, this, this one is a quartz-rich layer with different fabric. Okay, the S are quite convincing. There's also some see structure, maybe this one, this one, this one. In the field, it is not so easy as in the picture of the book to recognize sense of shear. But with S fabric and C fabric, we can assess a sinistral, destral, sinistral sense of shear. Okay. This is part of the huge shear zone that we call the East Variscan shear zone that crosscut Sardinia, Corsica, Morse Esterel, Argentera Massif in the Western Alps. So it, with a length of maybe more than 1,000 kilometers. Active sorry, boundary. No, the problem of this shear zone that the thickness is 10 kilometers. So we are inside. This is a quartzite-rich layer with a different fabric, but it is not the boundary. If we take a scene section here, you can see the orientation of quartz, quartz preferred orientation, also some rotated porphyrio cluster. So it is a different rocks with same similar deformation. Okay. Okay, you can see here in this scene section something similar to C fabric and S fabric. Mm. But is it a real uh, shear band cleavage or compression and connection cleavage? What is the difference? Difference is this one because when you have folds or superposed folds, you have several foliations, and in this case you have an older foliation, this one, deformed, folded, and the new foliation, this one, that is a granulation cleavage. But these cleavage are not related to shear zone, to displacement, but are related to superposed folds, two generation of folds. The F1 folds giving rise to this foliation, and there's a second generation fold giving rise to this generation cleavage. So we are in a context completely different from the shear zone. This is a fabric in a shear zone, also from Sardinia. You can observe the C structure, the S structure, but what is the main difference in between these two pictures? Hmm, okay, so exactly. Exactly. In this case, the angle in between the foliation, the S foliation and the C foliation is from 0 to 90 degrees up to 0. So you have several orientation of the folded foliation. In this case, the angle in between the S foliation and C foliation is not larger than 45 degrees, and then try to become lesser and lesser. So this is strongly asymmetric. This is mostly symmetric. And in this case, we have folds inside. Here you can have folds, but uh, small scale folds like this, but inside the S fabric. Mm. So the shape is totally different, but it's very important to distinguish these two cases because also in published papers in the last year, so also in this year, some people make confusion between this kind of fabric and this one. And maybe one take this feature and we can say S, sinistral sense of shear, instead there is superposed foliation by folds. This is a different history of the formation and a different, of course, displacement if there are. So in the book of Pasquier and Trau, you can see you can find some indicators distinguishing between the two cases. There are several indication, but the best one is the angle between older foliation and shear band cleavage, generally between 45 and 90 degrees in superposed folding. And the angle between all the foliation and the shear band cleavage is usually less than 55 degrees in shear zone. And there are also some other things that can help to interpret better the shear zone or not. Mm. Okay, oblique foliation. Oblique foliation, you can have this kind of kinematic indicators in myelonites because of the single grains, such as quartz, very common, is strained, deformed in very long ribbons parallel to the main foliation plane. Now, very whitish ribbons in the rock. This is the ribbons that you give a look inside. You can observe recrystallized grains like this that are elongate in the direction of extension and shortened in the direction of shortening of the finite strain ellipsoid. And this grain could develop a grain shape, the preferred orientation, that is a preferred orientation of the boundary of the perimeter of the grain, and also a crystallographic preferred orientation. That means that all the crystallographic axes are oriented more or less in the same direction. I will show you an example. Okay, this is a quartz myelonite. This is a main foliation. These are uh, the stripe reached of quartz, and you can see the quartz crystal are recrystallized, and you can see the shape like this, are oriented in this way, and they develop an oblique foliation with respect to the main foliation in the myelonite. There is obliquity of 45 degrees, 30 degrees, or less, because as its strain increases, the angle became smaller and smaller. And in this case, you can observe a shape preferred orientation because the grains are elongated. But if you put the gypsum plate under the microscope, or you can take measurements of the c-axis, you can see also the orientation of the crystallographic planes. This is another example: myelinitic foliation and oblique foliation. It's quite clear. Okay? And the oblique foliation is, of course, related to the sense of shear, because to have grain elongated in this way, you have a compression like this, extension like this, it means a sinistral sense of shear. This is a scene section from Khumbu, the southern flank of Mount Everest. I took this section several years ago, and there are rotated porphyroclast, but also quartz ribbons like this or like this. And you can observe different obliquity of the quartz crystal here that are more or less at 30, 40 degrees with respect to the main foliation, marked by the crystallized biotite and silimanite along these planes. In these ribbons, the quartz is almost parallel to the foliation, because in each panel, the formation is more or less independent. This started in this way and was frozen in this position. This deformation started in this way, then rotated and was frozen in this position, and so on. So in different parts of the scene section, you can see the same kinematic indicators, but with different angles with respect to the myelinitic foliation, because it is like a clock. Uh, it reaches 0, 1, 2, 12, then start again. So the formation start in this way, the grain rotate, 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 then recrystallize, start with a new position at 45 degrees, then recrystallize again. So this is a continuous process. And when the rocks is cooled and the fabric is frozen, you can have a different picture of the amount of deformation in each quartz ribbons. But the sense of shears is always the same, is concordant in the different part of this rock. Okay, other good kinematic indicators are the porphyroclast. That means you have big cluster, maybe 10 times more larger than the matrix. That can we can divide in shadow and mantled porphyroclast. The shape is the same, the geometry is the same, but with mantle porphyroclast, the famous sigma and delta of the Greek alphabet, means that the clast and the matrix and the mantle are made by the same composition. If this is feldspar, the tail is made of feldspar. If you have feldspar and the tails are made of quartz, you speak about a strange shadow. There's a small difference, but the kinematic indication is the same. And the other asymmetric porphyroclast is a mica fish, a crystal of mica with an S shape. Is a beautiful kinematic indicator, especially in granitic rocks deformed in simple shear on so on. Okay, we can to understand what happens. We need to give a look to the stiff inclusion, larger than the matrix, the porphyroclast, and the sense of shear. With this sense of shear, the strain ellipsoid is oriented with x-axis in this direction and z in this direction. So if you divide the stiff inclusion in quadrants, 4 quadrants, these one are extensional quadrants where material are extended. These one are the compressional quadrant. Okay, these are quite important because when you have a liquid mineral porphyroclast with sensor shear, try to rotate. If my hands are the shear zone, this porphyroclast, when I move the hands, the porphyroclast try to rotate in the same direction of the shear. If it is a simple shear, all the rotation is in the same direction. If you have non-coaxial deformation, pure shear plus simple shear, you have also opposite rotations. But in simple shear, the rotation is in the same direction. So these rigid minerals try to rotate. While rotate, you protect the matrix from the pressure, and if present in the strain shadow, some minerals could crystallize, such as quartz. For example, you can see here a crystal of starolite with the strain shadow made of quartz with an asymmetric shape, and of course the quartz try to grow in this direction, and in this direction then is moves parallel, is linear to the metric foliation. So at the end they assume an S shape, and this is the same also for the mantle porphyroclast. In this way, with this kind of shadow, the sense of shear is dextral or right lateral, and in this way the same, because you can have the lower part here, then a concave shape here, the straight part here, the concave shape here. So there is an asymmetry of the tails, and these are related to the dextral sense of shear. This is in Morse Massif in southern France, a continuation of the East Variscan shear zone that we found in Sardinia, with the same minerals, the same temperature, pressure, kinematic indicators. So in some cases, also at the outcrop scale, we can observe some asymmetric porphyroclast. But the best are observed at synsection. This is another strange shadow. In synsection, feldspar porphyroclast, mica crystals along the magnetic foliation, and the crystal of quartz that are growing in the shadow of the big porphyroclast. This is not easy to detect the sensor shear because the other part is lacking. So I cannot see exactly. I expect to have another tail in this direction, but in this position, but I don't know. So it's not easy in this picture. Okay. Now we can give a look to the best kinematic indicators that are the sigma and the delta ones, because there are several shape of the mantle porphyrio cluster. There are fish shape when the mantle are completely symmetric, or they are much more complex, but the best one are the sigma and the delta object. The sigma is stair-stepping. If you make a median line passing through the center of the porphyroclast parallel to the magnetic foliation, these tails doesn't cross the line. We start from the bottom on the right to the upper part on the left in a sinistral sense of shear, like this. The observation surface should be the XZ surface of the myelonite. And in this case, the mantle is very thick, huge amount of material from porphyroclast to the mantle. In the delta object, the situation is different. You can start from the lower part, then the mantle is very thin, it cross the median line and they reach the upper part, then it moves to the lower part, cross the median line, and move in this direction. And these are connected to the sinistral rotation of the porphyroclast. In this case, are stair-stepping. There is a different in altitude with respect to the magnetic foliation, and this is a delta object with a non stair-stepping. So the tails start along the foliation and finish along the foliation, but the rotation is the same. Here we can see a synsection of myelonitic granite in Bhutan. We are in the Great Himalayan sequence. These are leucogranites more or less deformed 20 million years ago. We had some datation, and you can see big porphyroclast of feldspar with the picture is with parallel nickels polarized, only one polarized, and you can observe one sigma shape porphyroclast, also this one sigma shape. There are also smaller porphyroclasts. That means that the deformation is not uniform in section. Less deformation here and much more deformation here. Maybe protomyelonite and myelonite. So deformation is very heterogeneous also at the centimetric scale. In this case, you can observe sigma shape porphyroclast like this. But the problem is that you have several porphyroclasts close each other. So everyone is not free to rotate and to develop the tails or the mantle, but there is interference between different different porphyroclast. There's collision between porphyroclasts. So we should be you should take care of observe porphyroclasts that are free to rotate and pay attention not only to one porphyroclast but to several porphyroclasts or several other kinematic indicators, because especially when there is a component of pure shear, you can have also rotated porphyroclast in the opposite direction. So only one may be confusing. Two are very, very few. You need to use dozen of porphyroclast. This is a beautiful Norway porphyroclast. This is a porphyroclast. You can see beautiful tails here. Became thicker in this part, then moves in the upper part. This is a sigma type porphyroclast with sense of shear, dextral, sinistral. Is better sinistral sense of shear, because you put the material in the elongation direction, then it moves parallel to the foliation. And to elongate in this direction, you need shortening like this and elongation like this. That is related to the sinistral sense of movement. This is a big porphyroclast in the Makalu orthognathus in the upper part of Greater Himalayan sequence in Nepal. With my finger, you can see big porphyroclast. What do you think? Delta, sigma? Sigma, okay. And the sense of shear is sinistral. Okay, yes. Sometimes there are problem because porphyroclasts too close each other, but with increasing strain in the direction of compression, the porphyroclasts tend to be close together. This is a picture from a big shear zone in the crystalline massif of the northwestern Alps in the French side, not far from Turin. We are only 60 kilometers away from France. So this big shear zone is in between and Italy, but in France it is well exposed. And here you can see a beautiful porphyroclast, rounded, is a tail here. There are also some shear band here, some C-plane. So the porphyroclast is of sigma type, and the sense of shear, dextral one. Dextral one. In this case, the foliation is almost vertical in the outcrop, and the dextral sense of shear is recognized all along the shear zone from uh, Sardinia, Mors Massif, Argentera Massif, Agui Rouge Massif, all the massif in the northwestern part of the Alps. With the same attitude, vertical foliation, subhorizontal stretch inclination, and dextral sense of shear. It's very, very constant. Okay, this is the other part of the porphyroclast that I showed you before. This composition is different. It's quartz, feldspar, quartz, so we can speak about a strange shadow. The sigma type. You can see also the tails are very huge in this part, they thinner in this direction. You can see this part is straight, this concave and straight. So this is also an example of dextral sense of shear. This is a dextral porphyroclast. The picture made by Pasquet maybe in Namibia. Is in the book. Is a beautiful delta porphyroclast. You can see the tails coming up, down. Is not maybe stair stepping, but this indicate a rotation, a dextral rotation of the porphyroclast. You can try to draw a median line from here parallel to the foliation, intersect the median line here and here. So it is the dextral one with dextral sense of shear. There is also a nice fold here with a long limb, short limb, and a long limb. The folds are sometimes used as shear sense indicators, but they are not so good because uh, in this case there is an agreement between the fold and the porphyroclast, but sometimes asymmetric folds like this are found also in sinistral shear zone. So the folds are the worst kinematic indicators, and we can use the folds in accordance with other indications such as SC fabric, sigma, delta, porphyroclast. Okay, this is an experiment made by Coin, a German geologist, made with camphor. Camphor is analog material of rock, but can be deformed under the microscope at room temperature. And you can see here the rotation of the porphyroclast, continuous rotation, and the development of these thin delta type tails. Okay. You can see again. Is a good example. Okay, these are in the same rocks I showed you before for quartz ribbons. In these rocks, you have also heterogeneous deformation because here you have a lot of porphyroclast, a small amount of matrix. Here you have a lot of matrix and a few porphyroclast with smaller dimension. So there is heterogeneous deformation. Here you can see two delta type porphyroclast. This one a little bit, some asymmetric folds like these. These are quartz ribbons, the ones that I showed you before. The rock is gneiss with biotite and sillimanite. We are in the Equator Himalayan sequence, the metamorphic part of the Himalayas. Okay, so the sense of shear, what do you think? Extral, okay, extral sense of shear. Perfect. Here we can see some movies from Fossen explain if you look at this line, you can see that this sigma porphyroclast rotate a little bit. In this case, the delta porphyroclast rotate a lot. This is the main difference in between the sigma and delta, because in the sigma there is more rotation and large amount of crystallization. In the delta porphyroclast, we have a lot of rotation of the porphyroclast and a small amount of recrystallization. In fact, the tails are very thin. There are also some other mechanisms to explain this kind of behavior that you can find in the Pasquier-Trau book that are related to the type of flow. It is a little bit complex because they try to explain by the mechanics of fluids. It's not easy, but there are much more details about these kind of tails. Anyway, these are very useful to detect the sense of shear. Oh, sometimes there are structure named the rolling structure, like Rolling Stone, the music band. It is different, but you can have delta tails and sigma tails in the same porphyroclast. Why we can find this kind of feature in one single porphyroclast? Because maybe the porphyroclast change the velocity of rotation. Because, for example, when you have a porphyroclast inclined 45 degrees to the shear plane, there is a maximum velocity of rotation. But when a porphyroclast is close to the shear plane, it rotates very slowly. So it depends on the initial orientation of the porphyroclast and also on the aspect ratio, because if a porphyroclast is rounded, it rotates very easily. If a porphyroclast is elongated like this, it rotates and parallelize the shear plane and stay in a stable position. So there are several factors affecting the rotation of porphyroclast. And if you start to rotate slowly, then the rotation increase, you can develop sigma tail and delta tail. So the opposite, if you start with a high velocity and the velocity decreases. So it is common to observe also this kind of feature in the metamorphic rocks. In this case, the rotation is always in the same direction, so the sense of shear is top to the right. So no problem. Okay. Another kind of good kinematic indicators are the snowball garnet that are very common in metamorphic rocks. This is a garnet with a foliation outside and inside the garnet. This means that porphyroclast has rotated 90 degrees. This porphyroclast of garnet have a snowball structure. The foliation is rotated several times, and in this draw you can see the concept. You have you can start the growth of the garnet and the rotation because you are in a condition of simple shear or coaxial deformation. So the garnet growth includes the foliation, rotate, and then the growth increase and the garnet became larger, larger, larger. And at the end, it depends on the amount of rotation. You can have a snowball structure like this, very complex, or in this case, you have a rotation like 90 degrees. So you have this picture like this one. So 90 degrees rotation. If rotation continues, you can rotate 90, 180, and so on, 360. So it is the case of synchronic mineral rotating during its growing. The last kind of porphyroclast, asymmetric porphyroclast, is the mica fish, or fish in general sense, because you can have also kyanite mica, kyanite fish, but the most common are white mica or biotite fish. In this section, you have quartz with an orientation like this, and a sigma shape mica, white mica fish, with tails with recrystallized mica with a smaller size, and the smaller size is also around the big crystal. And the geometry is like this. Is the original mica fish, is sigma shape, and the recrystallization of mica fragments or separation by stretching, micro shear zone, similar mechanism. So in this case, crystal like this indicate a distal sense of shear, like this one, but it is important to take in mind that this is an old porphyroclast. The new one are these smaller along the foliation or outside along the boundary of the porphyroclast. Because if you try to give geochronological information about the shearing, maybe by laser ablation to detect potassium, argon ages, you cannot use this porphyroclast, but this one to detect the shearing, the age of the shearing. Because also in literature, some people use this large porphyroclast to detect the sense of shear, and the sense of shear, of course, is okay, but the age of the shearing is not good because this is previous of the shearing. The minerals that grows contemporary to the shearing are the smaller one, this one. So you have to use a laser ablation to detect the position and to date this crystal, this one, this. Got un po' di confusione. Okay. So it is very important because sometimes in the paper you can find ages, numbers, but not all the numbers are related to the right process. So you have to take care of this situation. The shape of the mica fish could be a little bit different depending on the orientation of the original mica with respect to the shear sense. So in the book of Pasquier, you can find the percentage of different kind of mica fish. It depends also on the basal cleavage of the mica. It is parallel to the foliation, is oblique, inclined on the positive direction. But in any case, part of with this group that show a shape in an opposite direction, the group 1, 2, 3, 4, 5 are good for to detect the sense of shear. Okay, so the tails that formed during deformation are due to sliding along basal plane, rigid rotation, or boudinage of the tips of the mica and the recrystallization. So there are different mechanisms about this. So you can have also a crystal like this with a small fracture and the shearing. So the shape could be explained in different ways, but in any case, mica fish are very, very good. These are other examples with the basal, mm, um, the basal cleavage is parallel to the foliation. This is a little bit inclined. So the shape is a little bit different, but the sense of shear you can detect is the same. And also you can observe also a little bit oblique orientation of the quartz grains that confirm the sense of shear. Is a Carboniferous granite in Sardinia with beautiful mica fish. This is also the eye of the fish, the tails. And in this case, it is very interesting because you have recrystallized mica, recrystallized quartz like this one, and fractured feldspar porphyroclast. This is particularly interesting because quartz became ductile at 300 degrees of temperature. Feldspar is ductile above 550 degrees. So means that this deformation at the first sight is between 300 and 550 degrees. So without other information, we can give a look of the position of this deformation. And in this case, the sense of shear is again a dextral one. And this is belong to the system of dextral shear zone affecting the Variscan basement in Sardinia. There is a big shear zone in the northern part of Sardinia and another dextral one belonging to the East Variscan shear zone, and another one in the middle part of Sardinia, dextral one also belonging to the same system with the same age, but with a different position. Okay, this is the Ordovician orthogneiss in the northern part of Sardinia, the shear zone, feldspar, biotite. What you can see here, some mica fish, biotite fish, some SC fabric. So these are more or less biotite fish. Is a little bit beautiful respect to the others. So the sense of shear is, c'è scritto? No, Dex. Good. Dex has sense of shear. Ah, we are not far from here, the Mugu Karnali area in between India and Nepal. We are in the Greater Malayan sequence. And this is a shear zone inside the metamorphic core that I will show you in the next days. This is in the middle part of the Greater Malayan sequence, and there are several kinematic indicators, and also this white mica with a quite nice shape, indicating a dextral sense of shear. But in the field is the top to the southwest sense of shear. Is a thrust sense shear zone. Mm. Okay, another distinction is between mica fish and foliation fish is mica fish or fish, mineral fish, granite fish is related to one single mineral deformed in this shape. When you have an aggregation of minerals, an aggregation of foliation, you can speak about foliation fish. There's just a small difference in nomenclature, but the meaning is the same. If you have two or more mica crystal, you can talk about foliation fish or similar. Quarter structure, you remember the quadrants that I showed you before. Sometimes the foliation is wrapping around the posterior cluster and is rotated in this extensional quadrant. The compression is like this, so you have an asymmetric fold here and a symmetric fold in the opposite quadrant. And these are related to the same sense of shear. And there are also there mats that are made by compression in this part of the posterior cluster in the compressional quadrants. You can observe sometimes accumulation of mica or myrmecites in this part. So, okay, this Akunfossen show us how asymmetric fold, quadrant fold are developing. So, okay. ISA, do you know what is ISA? It should be instantaneous stretching axis. I spoke about finite strain up to now, but more correctly, we should speak about instantaneous stretching axis. The deformation that instantaneously happen in each increment of deformation. After an amount of increment, you can speak about finite strain, but more correctly, we can speak about instantaneous stretching axis, instantaneous elongation, and instantaneous compression. These axes are constant. Then, after a while, the instantaneous stretching axis rotate and became a finite strain axis. So the finite strain increases, but the instantaneous stretching remain more or less the same. Okay. These are quarter structure. This is a feldspar porphyroclast, and these are myrmecites with a cauliflower shape here. And they are developed in the compressional quadrants of the porphyroclast. Not here, but in this direction where is the compression. So in this case, this asymmetry suggests a dextral sense of shear because we are more, or, more or less in this situation. In this situation. Maybe. So here you can see in the previous picture, you can see some folds in the extensional quadrant here, here, and here. So also the folds in extensional quadrant are in agreement with the rotation of the porphyroclast, and also the myrmecites came from some crystal in the same section. So there are several indications in agreement each other with a sense of shear. Okay, the last one is asymmetric boudinage. When you have a stiff material that became deformed in a matrix, maybe leucogranite in mica schist or dolomite in pellite, you can have a different deformation, and the difference in between the shape is the shear bend boudins and domino boudins is that domino boudins are more similar to square because there is a strong competence contrast in between the matrix and the layer. So there is a fracture, a strong fracture with antithetic rotation of the boudins like bookshelf. Mm. So in the sinistral center of shear, you can have antithetic rotation, and you have this high angle here in between these rigid blocks, okay? With with a sinistral sense of shear, sorry, with a destral sense of shear, this is the opposite sense of shear in the small fracture with respect to the destral one. In the case above, you have less difference in rheological contrast, in viscosity, in between the Boudin and the matrix, and the Boudin are a little bit deformed in a sigmoidal shape, and from one Boudin to another, there is a small shear zone at a small angle with respect to the shear zone boundary, with a sense of shear that is the same, more or less. It is similar to Riedel structure. Do you remember Riedel structure? The R1 at high angle, the R at a small angle. It is exactly the same, but in this case, they are useful as kinematic indicators. You can have some other feature, such as the matrix is deformed, is folded inside the space opened in the Boudins, like in this case. Could be the occurrence of some kink bands or some flanking folds with flanking folds are structure uh, that cannot be explained easily in a normal way, such as the uh, do you know a fault? If there are some layers at an angle to the fault, they are you can have in a normal fault some how do you say in English? Forgot the name. Help me. What is the name of the foliation where it become curved, closing, approaching to the fault plane? Trascinamento, ma in italiano. Okay. Have you some? Maybe I try to. Drag. Drag. Okay. Drag. Okay. If you have a fault like this, you can have a normal drag in this part and an opposite drag in this direction. But sometimes in the field, you can observe maybe inverse displacement of object and normal drag. So you can have holes or structure with the drag is opposite with the displacement. And this kind of structure are named flanking faults. And you can find some details in the book of Pasquier. And they usually are explained by non-coaxial deformation. You can have a shear zone, maybe the extra one, with a discontinuity in between the matrix. And with deformation, the discontinuity can rotate up to this position. And in this position, you can have a drag of defoliation that could be opposite to the sense of displacement. There are several kinds of this structure. They're not easy, but can be useful sometimes in the field to detect the sense of shear. Because sometimes one cannot explain the difference in displacement and drag of the foliation. Here we are in the Alps, in the metamorphic nappe, and you can see some stiff layers like this with this kind of Boudin. What do you think about this displacement? Is more or less shear band Boudins or domino? Yeah, shear. Shear. So if this is the plane of shear, is maybe synthetic, so the sense would be this one. Okay? Is It is another outcrop with limestone and dolomites. The difference in contrast, rheological contrast is very high. So you have domino budens. So you have this shape, and oh, it's not easy. It's maybe movement like this. So if it is antithetic, the sense of shear would be left, up to the left. But of course, it is not enough, one picture like this. You can go around, take sample, observe porphyrio class, because it's better to use several objects. This is from Fossen, um, domino Boudin, and also some asymmetric folds that point to the left sense of shear. Okay, this is a simple picture. You have a stiff layer oblique to the sense of shear, and during the formation, you can develop boudins along a previous structure or weak zone in the layer. You can have domino boudin and the shear-bend boudin also at a macro scale, because you can have rigid grains that can break in this hard grain with domino boudin like this on the right. So yeah, you can have domino fragmented porphyroclast with high angle fracture, static. So this is sinistral, and the general sense of shear is dextral. It's okay. Here's an example from the Cap de Creus shear zone in Spain, the famous shear zone studied by Spanish colleagues. You can observe a fespar porphyroclast with domino-like fracture, suggesting up to the right sense of shear. In this section, you can have also uh, small synthetic fracture and antithetic fracture, pointing to the same sense of shear. The main problem with this kind of indicators, if is that if the angle is very high, is okay. If it is very low, it's okay. But when you are 50, 60, you are in between, you cannot decide if you are at a small angle or at a high angle. So you can refer only to the end member. Because if you are in angles like this, you cannot decide if you are in one kind of structure or the other. Okay, these are other example of antithetic fracture in feldspar and plagioclase, and synthetic fracture like this. They give the same indication, and this is good. Okay, so okay, asymmetric fold. Asymmetric fold is the worst kinematic indicator. So this is an asymmetric fold in scene section in Sardinia, metapelite and metasamite. You can see long limb, short limb, long limb. So you can put a sinistral sense of shear. Some people use this one, but there is a simple experiment made by Fossen that you can start with a layer like this in a sinistral sense of shear. You start to develop asymmetric folds like this, but when the layer um, rotate in this direction, you develop asymmetric folds in the opposite sense. So if you look this outcrop, only this outcrop, you can say, okay, that's a sensor shear, but you cannot have information about the general history. And if you started in this way, you can reach this asymmetric long, short, long, with a different opposite sense of shear. So only folds are not good to use as kinematic indicators. Another feature of the shear zone is the occurrence of sheet folds. Sheet folds are folds, non-cylindrical folds, with the axis of the fold completely rotated towards the direction of the extension of the shear, because the direction of extension is a tractor of the fabric. So to the end, you have an axis that is like this, rotate completely and come back in this direction. And in section perpendicular to the elongation dilation, you have closed folds, I folds, like this. These are meta charts in alpine Corsica, formed during the subduction of the oceanic lithosphere. And you have this closed shape, and the elongation lineation in this direction, and also the axis rotate in this way. Okay, in this picture, Fossen explain. Some people use this for their kinematic indicators, but you can see that you can have an antiform here and a form in the part. So in reality, they're not good kinematic indicators. It is very difficult to detect the sense of shear. So it is better not to use this one. Okay, this is a same outcrop, and this is a 3D shape of the sheet fold. You can see the axis going here, here, and coming out from this part. Is this shape like a mushroom? Is not interference pattern, but it is due to the rotation of the fold axis during the shearing. In this final picture, you can see an evaluation of the kinematic indicators by Paul Bonds, a structural geology from Tübingen, very famous. And he put an evaluation of the reliability of kinematic indicators on the right. For example, he found reasonable asymmetric folds and very bad bookshelf structure. Depends on but for example, delta are excellent, sigma are good, shear bands excellent, S fabric good. You can see an overall view of this one. And in this final picture, you can see a recall of the kinematic indicator. So you can print and take in your uh, in your field work, just to remember the kinematic indicators, the shape, what they are, the geometry, just to have to be more confident in the field. Okay. Now in sections. Have you some questions about this? All right. Bene. Good. So now we move to the. Okay.